you can find the sign-up stuff there as well. So the first thing I want to do tonight before getting into any specific exponent questions, and if any of my students are here, this is something I like to do at the beginning of any exponent lesson I give, and that is I want to just draw out 3 main exponent rules, and we're going to be using these rules a lot in the webinar tonight, as well as some other rules. But these 3 main rules are going to be very helpful as we move forward through some of the questions I'm going to be providing. And 2 of the rules are related pretty well because they force you to use common bases, and then the other one is kind of its own rule. But it's when you have to add or subtract exponents, and when you're multiplying exponents that are the same base, you ultimately add the exponents, and when you divide exponents of the same base, you ultimately subtract the exponents. Now, the key item here is that we have the same bases when we're doing this. And the third rule, of course, is that when you have an exponent raised to, or excuse me, a base raised to an exponent, and it's raised to another exponent, you actually multiply the exponents. So these are 3 main rules here that I want everyone to make sure they have in their back pocket. And it's not just to say for tonight, but also obviously for when you're on the GMAT, because I think these are going to be beyond helpful if you can do these without really having to think about it. So the first question here is going to bring into play what I had just mentioned. And as always, I'm going to give everyone 2 minutes, and then we're going to talk about this rule, or excuse me, about this problem. And again, to give everyone a hint, getting the bases to be the same is going to be really important. And when you have the question answered, make sure to put it in the chat box so I can see what everyone is getting for their answer. Okay, does everyone hear me now? Okay, so what I was saying before was that in order to make this problem as simplified as possible, the goal is to get all the bases to be as similar as possible. Now, it's not to say that every base here is going to break down to the exact same thing, but we're going to see that there's going to be a lot of combining and canceling out that can happen. And in our exponents chapter, one of the main things we talk about is getting some of these exponents memorized, or numbers memorized as their prime bases, one of them being 125. Now, 125 is 5 to the third power, but you have to keep in mind that we're not just breaking down 125, but we're breaking down 125 to the second power. So 125 to the second power is 5 to the third to the second, and that, of course, gives you 5 to the sixth. Another exponent that we talk about memorizing here is 243. Now, 243 is actually 3 to the fifth power. Now, that, again, that's raised to the second using the third exponent rule I talked about. That's going to give you 3 to the 10th power. Now, if you didn't know that 243 was 3 to the fifth, certainly you could go a longer route in breaking it down. And in fact, I'll show you how to do that with 405, so we're all on the same page. But moving on to 16, 16, if you haven't memorized, is also 2 to the fourth power. But again, it's not just 2 to the fourth, it's 2 to the fourth to the third, because we have 16 to the third power. So this, of course, gives us 2 to the 12th. So at a bare minimum, we have our numerator, which is 5 to the 6 times 3 to the 10 times 2 to the 12. And the final thing we have to break down is our denominator. Now, our denominator is 405, and this is not a number that we have necessarily memorized. So if you're on the test and you're thinking, okay, well, how can I break down 405? Well, the quickest way to think about it is to look at the units digit and say, well, we know 405 is divisible by 5. And if you can't do it in your head, then, maybe it takes even a brief moment of long division where you say, okay, well, 5 goes into 40 8 times with 0 left over, and it goes into 5 once. So we know that 405 breaks down to 5 to the 5 times 81. Now, 5 is prime, so we can stop there. Then we need to break down 81. 81 is actually 3 to the fourth power. So if we set this up, we have 5 to the 1 in the denominator, and then we have a 3 to the 4 in the denominator. Now, what's interesting is already you could basically look at your answer choices and say, well, there's only 2 answer choices that have a 2 to the 12 in it. So we can easily eliminate C, D, and E. And then finally, if we want to use our exponent rules of divisibility, 5 to the 6 combined divided by a 5 to the 1 is going to give us a 5 to the 5. 3 to the 10 divided by 3 to the 4 is going to give us a 3 to the 6. And then that's going to leave us with 2 to the 12th power. So the answer here is A. Now, what I want everyone to keep in mind is we didn't, reinvent the wheel here. We just used our exponent rules as I showed you originally. The key component here, though, was getting everything as simplified as possible. And, given that this is our, I believe, 4th webinar, you've probably heard the word simplified a lot. And it just goes to show that regardless of the topic, making things as simple as possible on you is going to be the easiest way to deal with these questions. So what I want to do now is I want to keep the same theme going, but I want to transition into a little bit more of algebra with these exponent questions. And you're going to see how that plays a role as well. Still, prime factorization is important. So let's try this question here. And again, as you get the correct answer, make sure to type it into the chat box, and I'll give everyone 2 minutes. All right, well, that again was about 2 minutes. I see we have one answer, and the answer posted is the right one. So hopefully when everyone looked at this question here, you noticed again that you couldn't really do much with the bases as they were presented, but if you were to simplify those bases, you certainly could start to combine, plus eventually get rid of things. So one question I get from students a lot is, how do I know what to get the bases, or how to simplify them down, or when to stop? And I mentioned this before, and I'll mention it again. It's going to be beneficial if you just say, I'm going to get these to primes, and I'll stop once they're primed out. So, for instance, when you look at 27 to the x plus 3, it makes the most sense to just get these all the way down until you're only working with 27 when it's in primes. And again, this is another base to have memorized, but 27 is actually 3 to the third power. So you have 3 to the third to the x plus 3. Now, this may be a little confusing, but remember, same math rules apply. You have a parentheses here. You need to use the multiplication rule. So really what you're doing is you're distributing the 3 there, and that ends up giving you 3 to the 3x plus 9. And I would definitely recommend making sure that you have everything as simplified as fully as possible before moving on to your next base. Now, that next base is, of course, 9 to the 4. If you were to break down 9 and had that memorized, we know that that is 3 squared, but it's not just 3 squared, it's 3 squared to the 4th, and that gives us 3 to the 8th. Finally, we have our 81 to the 5th power, and again, this is another base to have memorized, and 81 is equivalent to 3 to the 4th power, but it's not just 3 to the 4th. Don't forget about the 5. It's 3 to the 4th to the 5th, giving us 3 to the 20. So now you'll notice we have everything right where we want it. We have everything down to prime bases, and in fact, we have the same prime bases. So using rule number 1 that I taught you, when you have the same bases and you're multiplying, you can actually add the exponents. So the next best thing is to take 3 to the 3x plus 9 and add the 8 to it. Now, you always have to be careful here, because I realize that the bases are being multiplied there, but you're actually adding the exponents. And more times than not, I see students making the mistake of multiplying 3x plus 9 by 8 instead of adding the 8 to it. So when you do add the 8 to it, you get 3x plus 17. That equals 3 to the 20. Drop your bases. And this is important, because at this point, where you have the same base on either side of the equal sign, you're allowed to drop those bases and equate the exponents. And so now what we have is a very simple equation of 3x plus 17 equals 20, 3x equals 3, and of course, x is 1. So this is a very systematic process you can follow when you see that algebra is being involved with any sort of exponential equation where you're multiplying the bases as you see here. And step 1 is always breaking into primes. Step 2 is combining once those bases are in similar bases. And of course, step 3 is dropping the bases when applicable and solving for your variable. So what we're going to do is we're going to continue to do questions in this neighborhood, and then I'm going to pass it off to Scott so he can get into some more challenging questions. So as always, I'm going to put 2 minutes on the clock. And again, this problem definitely is testing you on your ability to prime factorize. And just take your time, because any small mistake can really change the outcome here. So I'll give you guys this next, and put your answer in the chat box as you start to come up with it. Okay, so that was actually over 2 minutes, but I wanted to give everyone an opportunity to try and do this one out to the fullest. So I'll start explaining the problem. If you do get the right answer as I'm talking, feel free to, put it into the chat box so we can see what you got. This is an interesting question here. You'll see why in a moment, but it's interesting because it's a little bit more complicated than the last one we did, but the process actually doesn't change at all. And this is why I love exponents in general on the GMAT, because I find that it's a very systematic or black and white process, and it doesn't change all that much for different problems. So what we would do here is we would first take the 24, and as I showed you before, we would prime factorize it. Now, 24 is the first number we've seen today, or first base, besides 405 in the first question, that actually doesn't have just one, doesn't break down to just one prime base, and we're going to see that in just a second. So if I'm prime factorizing 24, I'm going to take any number that divides into it. So let's say 3. Well, we know that 3 times 8 is 24. What's nice about this is we can now take the 8, because that's one of the bases worth memorizing, and say, well, that's 2 to the 3rd power. So if you look at what we have here, we have a 2 to the 3rd, and we have a 3 to the 1. Now, remember, it's not just 3 to the 1 and 2 to the 3rd. It's 3 to the 1 times 2 to the 3rd, all to the 4th power. Using the 3rd rule, we have to distribute the 4 into the parentheses. That gives us 3 to the 4 times 2 to the 12. And then we leave that alone and we move on to the next value, 16. Well, 16, as we know, breaks down to 2 to the 4th power. So we have 2 to the 4 to the x plus 3. We know from previous problems that we distribute the 4 outward using multiplication, and then that gives us 2 to the 4x plus 12. Now, lastly, on the right-hand side of the equal sign, we have our 18 to the 2nd power. We break that down. 9 goes into 18, so we can say that's a 9 and a 2. 9 is, of course, 3 squared. So we have 3 squared times 2 to the 1. And again, we can't forget the 2. And we distribute it. And that gives us 3 to the 4 times 2 to the 2. Now, the thing I said at the onset of this problem is I said this problem is a little bit more unique and interesting than the ones we did prior. Well, what you'll notice is we have bases on the left, and we have bases on the right. And they're different bases. They're not all the same this time. But you'll also notice that the 3 to the 4 here is the exact same as the 3 to the 4 here. What's important about that is that the 3 to the 4s both cancel, because you can divide both sides by 3 to the 4. That would cancel them out. And now we're just left with what we had before, which is a nice simple problem with the same base. So if we take our exponent rule, and keep in mind, everyone, I'm scrolling down here as I finish this, we are trying to combine, we need to first combine 2 to the 12 times 2 to the 4x plus 12. Again, that's rule number 1, so that's going to be 2 to the 24 plus 4x, and that's going to equal 2 to the 2. As I told you before, once you have same bases on either side equaling each other, you're allowed to drop those bases because the exponents themselves must be equal. So now we have 24 plus 4x equals 2, or 4x equals negative 22 from subtracting both sides by 24. And then finally, dividing both sides by 4, we get negative 22 over 4, or x equals negative 5.5. And for those that got it, that is answer choice D. So to reiterate here, we haven't changed a lot. We took a problem that had unsimplified bases. We got them into prime factors. We simplified where necessary, we canceled where necessary, and then eventually we dropped the bases and solved our unknown. So let's do one more here, kind of in this realm, and then I will pass things off to Scott. And as again, I'll put about 2 minutes on the clock here, and then we can talk about the solution here. Okay, so that was about 2 minutes, and this is a great question, and again, I can't tell you right away, but you'll see why as we get down to answering it. But there's a little twist in this question that we didn't have in the previous ones. So the first thing I want to do here, which is not surprising to anyone, is I want to prime factorize or get everything as simplified as possible. So the 7 to the 31, that can't be touched. But the 8 to the 10 can. Now, 8 to the 10, based off of having this memorized, is 2 to the 3rd. So that is 2 to the 3rd to the 10th. And that gives us 7 to the 31 times 2 to the 30th power. Now, if we go to the right-hand side, you'll notice we have a 7. Because I know that we're dealing with exponents here, it makes the most sense for me to say that this is 7 to the 1. So I don't forget that that's actually raised to a power. As far as 14 to the n is concerned, and I'm just doing this over to the side in case you can't see that, that's just 7 to the 1 times 2 to the 1. Since it's to the n power, that doesn't change the fact that we use our multiplication rule, which is rule number 3, giving us 7 to the n times 2 to the n. Now, what's great about this question here, or at least let me finish this up. So this gives us 7 to the 31 times 2 to the 30 equals 7 to the n plus 1 times 2 to the n. So why is this problem different? Why is this problem unique? Well, if we go back to the last question real quick, I said that we had 2 bases. We had the 3's to the 4, which I'll highlight in yellow real quick. Well, what happened to those extra bases? They canceled, and that's because we had a 3 to the 4th power on one side and a 3 to the 4th power on the other side. We were able to divide by 3 to the 4 and cancel them. Well, what's different here now is we actually have a base of 7 on the left and a base of 7 on the right with an n. And then we have a base of 2 on the left, which I'm highlighting in green, and a base of 2 on the right. But notice we can't cancel any of those bases out. But there is something else we can do. We can make equations that relate the bases of 2 with their counterpart on the right-hand side with the other base of 2, and the base of the 7 on the left with the base of 7 on the right. The good news is no matter which equation you create, you're going to get the same value for n. Now, because I like to make life easy on myself and I want everyone else to as well, let's go with the equation that has less going on. Clearly, that's going to be the one with the 2's because we literally don't have to do any math. We drop our bases. We get 30 is equal to n, and that's answer choice B. So in conclusion, with everything we just did in the first few problems, you're not going to get too far if you don't start by simplifying. So make sure simplification is always something you're looking to do. You're always trying to look to get the bases the same, and then you'll figure it out from there. The way the GMAT works, the way exponents work, you're not going to necessarily see the finish line when you first start the question, but if you stick to the same process each time, you remain systematic, you will eventually get there. So if something seems confusing at first, don't immediately give up. So I am going to pass the reins over to Scott, and he's going to continue with some more advanced exponent problems and exponent techniques. So Scott, you can take it away.
Okay, thanks, Jeff. Can you hear me okay, Jeff?
Yeah, I hear you just fine.
Okay, great. Very good, good. Hey, guys, thanks a lot for coming tonight. So what we're going to do now is we're going to build upon some of the skills and strategies and tactics you guys have just been practicing with. And the good news is a lot of what we do now is going to just rest on many of the basic yet really high-value skills that Jeff just went over with you. Just remember, guys, as always, our theme here is simplicity over complexity. Anytime something seems complex to us on the GMAT, our goal is to look for the most simplistic solution possible. And sometimes the way to do that is look at it through the eyes of a kid, like a child, like a middle schooler. Because as adults, we have the tendency to look at things and find what's wrong with them and find the complexity that exists within them. But if you notice, when kids evaluate a problem, they evaluate it under the most simple grounds possible, and that helps them tremendously. So I want you to keep that in mind, okay? Now, exponents, just like many, many, many other aspects of the test, are all about pattern recognition and the ability to move between different forms of the same thing, right? So for example, right, you now know that if you have a to the b multiplied to the c power, right, raised to the c power, you now know that's the same thing as a to the b times c. And this is a very simple example, but I want to use it to drive an important point home. On the test, if they give something to you in this form, you can bet your bottom dollar it's unuseful until you move it into this form, or vice versa. Okay, and this is where the pattern recognition comes in. Right? If they give you x to the a multiplied by x to the b, well, you can be pretty sure that the useful form is when you have x to the a plus b. They want to see, can you move from this form to its counterpart, or vice versa. And as Jeff told you, exponents are super mechanical. And if you can master these guys, if you can move between the different forms of the same entity, you're going to be way ahead of the curve. So with that said, let's get some more problems under our belt. Let's give this guy a try. It's going to build upon some of the skills you've already learned and then maybe test a few more. So when you do this, let's look for simplicity. Let's try and make this as simple as possible, and we'll shoot for about 2 minutes starting now. Okay, guys, that's actually about 2 minutes and 30 seconds. I wanted to give you a little extra time. Now, as I say every week, the time pressure here is a lot because we're trying to do a number of problems and we're trying to keep close to 2 minutes. During your self-practice, this might take you 3 or 4 or 5 minutes as you start. Okay, so if you can't do it in 2 minutes just yet, don't worry about it. Okay, so let's go through this, guys. So all about pattern recognition. Okay, so what I want you to see is on the left side of these parentheses, we have 4 5 raised to the 2ab's being multiplied. Now, this is a key signal to you, the factor. Remember, a couple weeks ago, we went through factoring and why it was important. And it's going to come back to roost right here. So what I would do is I would definitely factor out a 5 to the 2ab, okay, because it's screaming for us, it's begging for us to do that on the GMAT. And what we leave behind, if you notice, are just 4 1s, right? Because when you pull something out of itself, you leave a 1 behind. Okay, so let's just call that what it is. That's 5 to the 2ab multiplied by 4. Okay, we can do the same exact thing on the other side. Notice those 5 multiplications of 4 raised to the 2ab. Well, it's screaming for us to pull that out. So we'll say 4 to the 2ab. And again, I'll do it out this time so you see it. E 2ab out of itself, we leave a 1 behind. A lot of students make the mistake and do a 0, but it's not. When you pull it out of itself, you leave a 1 behind. Okay? So then this breaks down to 5 to the 2ab times 4 times 4 to 2ab times 5. But they're almost never going to give you something in the form that's right for you. So you're going to kind of have to mentally twist things around a little bit to get things in the position that makes the most sense for your brain, you know, however that is at the moment. Well, what I would remember is the order of multiplication never matters. So I would probably, if I needed to, I would probably remind myself of that fact by moving the bases of 5 next to each other and the bases of 4 next to each other. And why did I do that? Well, by doing that, we can see we can apply one of the rules that Jeff taught you, which is when you multiply bases that are the same, you keep the base and you add the exponent. And you may even want to write the 1s there just to sort of remind yourself. So this becomes, on the left, this becomes 5 to the 2ab plus 1. And on the left, on the right rather, this is 4 to the 2ab plus 1. Okay? So you've seen most of this up until this point. But now, what do we do? So we have bases of 4 and 5, which are dissimilar. But if we take a look at the exponents, we can see that the exponents are actually the same. And this is an important rule. So whenever we have the same exponents, what we can do is we can keep the common exponent and multiply the bases. So the answer to this problem is 20 to the 2ab plus 1, which is answer choice E. Okay, so in that last step, all we did is we said if you have 2 numbers or more, but in this instance 2 numbers, and the exponents are the same, you keep the exponents and you multiply the bases. All right, let's give it another problem a try. Let's do let's do this guy. And we'll set our timer. We'll probably go a little over 2 minutes, but let's give 2 minutes a try starting now. Okay, guys, that's about 2 minutes and 30 seconds. So this is a pretty common structure that you're going to have to get used to seeing, recognizing, and dealing with. So we see the two bases of 7 on the left-hand side, and there's a suspicious base of 7 on the right-hand side as well, which I want to draw your attention to, the 7 to the 6th. So on the left-hand side, and let me tell you guys something too. So when you have, let's just break this out for a second. So when you have something like this, there's no way to subtract these terms. A lot of starting students, and actually even some advanced students, they'll say, ooh, there's a way to subtract these guys. No, there's really not, especially without, especially with a pen and paper, there's not. So subtraction of exponents like this, and addition for that matter, is all about looking for a factorable opportunity. Okay, and this is a very factorable opportunity. So we're never going to try and subtract those. Instead, what we're going to do is we're going to try and pull a common factor out. Okay, so I'm going to rewrite this. I want you guys to look really carefully as I start the next line. And this is going to help you to see a little bit more about what I meant when I said you actually have to re-express things. So as I look at the left side, I don't know about you, but it's not really clear to me what the common term is. Okay. However, if I start playing with some of the exponent rules, just doing something, keeping my feet moving, it's going to be a lot easier. Well, I want to focus on that 7 to the x minus 1. If you think about it, that's an exponent rule sort of in reverse. Right, so 7 to the x minus 1 can be expressed as 7 to the x multiplied by 7 to the minus 1. I'll get back to that in one sec. Okay, so the transition from this structure here to this structure here, I think, is imperative to being able to solve the problem. Because at least in line 2, I can now see that 7 to the x is clearly the common term. But in line 1, I really couldn't see that. So this is so important, guys. I'm going to break this out on the right-hand side in red so you see exactly what I'm saying. So when you see 7 to the x minus 1, I would almost instinctually, unless there were compelling evidence to not do this, I would almost instinctually express that as the rule just written the other way. So these guys are two sides of the same coin. They're exactly the same, they're just written a little bit differently. And I encourage you to keep that in mind whenever you're doing exponent problems. Okay, so what that means is I am going to now pull 7 to the x out of that equation on the left-hand side. Now watch carefully, because everyone, if you're not used to this, it's going to be slightly confusing, but watch really carefully. So when I pull 7 to the x out, I'm going to immediately put in some parentheses here so I can visually see what's going to be left after that 7 to the x comes out. Well, when I pull 7 to the x out of himself, I'm left with a 1, right? When you take 7 to the x out of 7 to the x, there's a 1 that's left in the wake. Okay, so the minus sign is still here. That hasn't changed. And now when I pull the 7 to the x out of the yellow term, right, if you will, the yellow term, well, I'll be left with 7 to the minus 1. Okay, now let me break that out too, because a lot of students are unsure about this step. I'll do it in red as well. The key to checking your work is you must be able to distribute, we would say in math. You must be able to distribute the term you factored out back through and get back to what you had before, right? So I actually have to be able to multiply the 7 to the x back through the parentheses to get back to the line prior, which I can do. So we know the work we've done here is good to go. Okay, so I would rewrite this. This is 7 to the x times 1 minus, well, let's call it what it is. 7 to the minus 1 is 1 over 7. No need to keep things with negative exponents. Okay, let's just keep whittling it down. 1 minus 1/7, of course, is 6/7. Okay, right side of the equation, nothing much has happened yet. But what we're starting to see is there's a lot of symmetry between the left and the right side. So what I'll do is I don't like fractions, so I'm going to multiply the inverse of 6/7. So I'm going to multiply both sides of the equation by 7 over 6, right? And what that's going to do is it's going to get rid of the 6/7 on the left. Okay, so I'll have 7 to the x is equal to 6 times 7 to the 6th multiplied by 7/6, because remember, whatever we do to one side, we have to do to the other. Okay, and guys, make sure you're scrolling down too, because I'm below what was the initial field of view for everybody. So, okay, no worries there. So the 6's, you can see, cancel out on the right-hand side, and we're left with 7 to the x times 7 to the 6th times 7. Well, we're left with 7 to the x is equal to 7 to the 7, because remember, there's a 1 there. So as Jeff taught you really nicely, when the bases are equal, the exponents have to be equal. So x would have to be 7, and the answer choice is E. Now, it probably sounds or seems like a lot. And if you think back on your education, didn't most things before you master them, I mean, I remember sitting in math trying to do, multiplication, like 17 times 16, and I was like, what? Like, what is this? You know, teacher's trying to show you how to do that, and you're like, I'll never get this. And then, you know, a couple of days later, like, this is the easiest thing I've ever done. Same with this, trust me. The more you do this, the more this is going to become fluid, and the more you're going to see it. And remember, guys, you want to take advantage of the fact that the GMAT is pretty predictable. So if you can study the right stuff in advance, test day should be a formality for you. Okay, cool. So let's do another one. This is also fairly challenging. So let's set our timer for 2 minutes and see how we do. Okay, guys, gave you a little bit of extra time on that one. So which of the following is properly ranked in descending order from left to right? So again, you know, the theme here is simplicity. As these numbers are expressed, they're difficult to work with. They're really difficult to work with. You're never going to be able to eyeball them. I don't know, maybe you can, but it's unlikely you're going to be able to eyeball this and say, okay, this is the answer. You need a systematic approach. Here's what I want you to notice, guys, and this is a really handy approach for figuring out which ugly base to an exponent is bigger. 5 to the 50, 6 to the 25. Okay, what I want you to notice is that the greatest common factor of all of the exponents. So what's the greatest common factor? Well, just as it sounds, it's the It's the biggest number that will divide into both, all of 100, 75, 50, and 25. Well, the GCF, the greatest common factor of those four numbers, is 25, because 25 is the biggest number that will divide into all four of those numbers. Okay, so I want you to watch this really carefully so you see why we're doing this. What that means is we can raise each of these numbers to 1 over the GCF. And if you think about why it won't be intimidating, it will make perfect sense. And this will bring you all the way back to Jeff's power to a power rule he taught you early on in the lesson. Right? Because if you think about what this is, it's really now going to simplify down to something really, really, really simple. Okay? Because this is 3 to the 100 over 25, right? Because we're multiplying those exponents. This is 4 to the 75 over 25, because we're multiplying those exponents. This is 5 to the 50 over 25, because we're multiplying those exponents. And this is 6 to the 25 over 25, because we're multiplying those exponents. Okay, so really simple now. So this is 3 to the 4th. This is 4 to the 3rd. This is 5 squared. And this is 6 to the 1. And at this point, guys, these numbers are really manageable. Okay? These are obviously all numbers that we can work with. Okay? So pretty easy, right? So this is 81. 4 to the 3rd is 64. 5 squared is 25. 6 to the 1, of course, is 6. So let's see which one of these guys does it. We have to go back to the original numbers. So answer A, because we want descending order from left to right. Okay, so strategy here, guys. When you have a bunch of ugly exponents and maybe someone asks you to order them ascending or descending, it doesn't matter. You can raise them all to the GCF. And what you're going to see is they're all going to show their true colors to you, and you will be able to simplify them. Okay, guys. We could go on for days and days and days, but it's probably getting late for some of you guys on the East Coast. You know, I'm really glad you all came. Hopefully these webinars are helping you. Just remember, look for simplicity. Don't make things complex. Study the right stuff. Study the right materials. Look for simplicity here, guys. Don't make anything too big, too ugly. All of these problems have simple solutions. We'll look forward to seeing you back here, same time, same place, same channel, next Tuesday. Jeff, do you have anything you wanna add?
No, I think that was good. Thanks everyone for coming, and I sent the 2 links, one the feedback form, the other one is the link to sign up for our future emails. So no, thanks for coming everyone.
Okay, good night everybody. Take care.